Welcome to Pipes and Tubing. Let's take a look at the objectives for today's discussions. Today we are going to concentrate on objectives number 4 and on. I'm going to look at all of them shortly. First, I'd like to go over the objectives of last time, item number 1, 2, and 3. We looked at the volume flow rate, weight flow rate, and mass flow rate. And we also look at steady flow and the principles of continuity. And we also established a relationship between the continuity equation and the volume flow rate, area, and velocity of flow between 2 points in a fluid system. And that leads to the discussion of pipes and tubing and how we can actually design a basic system that includes pipes and tubing. We're not going to look at pumps because pumps are another topic by itself, but for this course we will stick to fundamentals of pretty much specifying the desired size of pipe or tubing for carrying a given flow rate of fluid at a specified velocity. Later on, we are going to take a look at the reasons why velocity is so important in designing pipes. And so we are going to take a look at recommended velocities of flow and typical volume flow rates for various types of systems. And of course, this lecture will not be complete without taking a look at some of the applications and also solve a numerical examples. Well, later on, we are going to look at item 8, 9, 10, 11, and 12 in the subsequent lectures. So we have different types of pipe and tubing. There are 5 main types. Let's start with steel pipe first. Steel pipe are the general purpose pipelines. They're for general applications, for specialty applications. They may or may not work. The standard pipe sizes are designated by the nominal size and schedule number. And shortly I'm going to discuss both of those, and throughout this lecture we're going to take a look at those in detail. The schedule numbers are related to the operating pressure of the pipe. Remember that the strength of a pipe is a key factor, so we want to make sure that the pipe that we use, they are a type of a structure. Of course, a pipe is considered to be a component of a structure. It is a structure itself, so we want to make sure that it is it can take the loads and take the stresses, and for that case we want to make sure that the allowable stresses of the steel is not reached. When I say they're a structure, they're different than buildings and other types of structures that we see, but a pipe is a structure that needs to be designed appropriate. The range of schedule is between 10 to 160. Again, the schedule numbers are related to the permissible operating pressure of the pipe and the allowable stress of the walls of the pipe, the steel that is used in building a steel pipe. So in a system, in this schedule system, the higher the schedule, that means the diameter, the inside diameter of the pipe would be smaller. The system of schedule numbers is also referred to as iron pipe sizes, or IPS. So you are familiar, you should be familiar with those terminology. Where do we use standard steel tubing for general purposes? Fluid power systems. We use them in condensers. We use them in heat exchangers. Also engine fuel systems. And industrial fluid processing systems. The application of them is also extended to sewage pipelines, but we use cast iron for those. Those are more popular. I'm going to take a look at those today as well. The sizes are designated by outside diameter and wall thickness. The standard size goes from 1/8 of an inch to 2 inches for several wall thickness gauges, and we're going to discuss those. Other wall thicknesses are also available. You can also order if the special pipe, special steel pipe, steel tubing is required. It can be ordered to the manufacturers, so it can be built. Of course, the cost would be much higher in that case. Let's take a look at dimensions of steel tubing. The outside diameter is given here in inches. The wall thickness is also given. Both metric and US customary systems are shown here. As you can see, the inside diameter is shown and the flow rate the flow area in square foot and square meter is also shown here. We're going to do an example, and we're going to look at this table in a more detail later. So the nominal pipe sizes are given in US customary. What if we want to convert them into a metric units? The table also gives a metric DN size. That's the nominal dimension or nominal diameter, but it's switched. DNN is switched, so it's diameter nominal. Actually, that's why it's shown in DN. This is standardized by an ISO, and of course, one must realize that we cannot directly convert these. We need to go and take a look at tables because there is no direct conversion in some cases here. Some of them we can do, but not all of them can be converted. Just getting the inches and converted to millimeters. So keep that in mind for the exams. Make sure you have the tables available so you can look these numbers up. If there's 1 inch US standard size is given, then you need to right away convert that to, for example, that'd be 25 millimeter, not 25.4. Again, you need to use the tables and do more practice, and it becomes much easier for you to do so. So, other types of tubing, a popular one is copper tubing. 6 types of copper tubing available: type K, type L, type M, type DWV, type ACR, and type OXY/MED. Let me start with number 6, the OXY/MED, used for oxygen or medical gas distribution. I started with that because those are, in some cases, they're a lifeline to many people. So it's important to discuss those first. They are also used in compressed, in medical devices where compressed medical air is needed, and in vacuum applications. They are available in sizes similar to type K and L, but special processing for those are needed because they got to be really clean and applied to people with special needs, people that need their lifeline. So let me go back to type K, used for water services, fuel oil, natural gas, and compressed air. Type L, it is pretty similar to number 1, but the wall thickness would be smaller. The type M is similar to either 1 and 2, type K and L, but the thickness is even smaller, and it is mostly used in for water services and heating applications at moderate pressures. It's very important. The word pressure here One of the key factors in picking the right size is, of course, the pressure for flow that are under pressure. We can also have gravity flow. In the case of sewage pipelines, they're gravity flow systems. So for those, we use cast iron and other types. For those, we also need to pay close attention to the lining. Type DWV is used for drain, waste, and vent uses in plumbing systems. And ACR is another type that's used for air conditioning, refrigeration, natural gas, and so on. So there are different, actually three main types of copper tubing: soft, annealed, or hard drawn. So it's commonly used as soft, annealed, or hard. Again, the hard drawn is, of course, much stiffer and stronger. It's more difficult to bend, and it can be used for higher pressure. Annealing tubing is easier to form into coils and other special shapes. The nominal or standard sizes for different types, K, L, M, DWV, and they are all in 1/8 of an inch less than the actual outside diameter. So if you have the nominal or standard size in let's say 7/8 of an inch, you need to add 1/8 to that to get 1 inch. That would be the actual outside diameter that we use in calculations. Remember, in calculations, we use the real diameter, not the nominal or standard, the given number. And that is because the nominal sizes are good for tabulation and all that, but the actual size is the one that we use in the calculation. Very important for you to realize. If you go out there to work in companies or what have you that design the system, that's probably the first question that the technical people may ask you. So make sure you guys understand that. The wall thickness are different for each type, so the inside diameter and floor areas vary. The third type that we're going to discuss here is the ductile iron pipe. Water, gas, and sewage lines are often made of ductile iron pipe because they're strong, because they're ductile, and they are relatively easy to handle. And the methods of building them, the methods of installing them, the methods of working with them is already developed. All the tools are pretty much in place. Remember that it is very important to realize that you may have a marvelous system of piping, what have you, but if you don't have the right equipment or the tools that are built to work with those, they really become useless. The ductile iron pipe has replaced cast iron in many applications. Again, there are several classes of ductile iron pipe are available for use in systems with a range of pressure. There are appendices in the book list the dimensions of class 150 pipe for 150 psi or 1.03 megapascal service in nominal sizes from 3 to 24 inches. Again, these are nominal sizes, not actual sizes. So one must pay close attention to the actual size and use those in calculations. Plastic pipe and tubing are also pretty popular, and they are lightweight, they are easy to install. One of the greatest advantages are corrosion and the chemical resistance. These are their advantages, not just one of them, but this is the wonderful advantages of plastic pipe and tubing. They have very good flow characteristics, and The friction is much less with the walls because of the smooth surface of the inside diameter. That's in case of non-corrugated ones. The examples could be water and gas distribution, sewer and wastewater, oil and gas distribution, irrigation, mining, and many industrial application. There are different types, polyethylene, PE, cross-linked polyethylene, PEX, and so on. They're all listed here, and many of them they're also used in the food industry as well. Many conform to existing standards of iron pipe sizes, of course, because they will need to compete. They are competing. The market for plastic pipe and tubing, they compete with other types of markets that are available for other types of pipes, so they need to be comparable, and as such, many companies they build these pipes as far as the size, they match the size for other types of pipes. Now, it is important to always look at the manufacturer's data because of the variations that do exist among plastic pipes. So for plastic pipe with a hydrostatic design stress rating of 1 to 50, the rating for different SDR ratings are as follows. And this is the little table down here for SDR and pressure rating associated with that. As the SDR, which stands for the standard dimension ratio, dimension ratio is based on a ratio, and that is the average specified outside diameter to the minimum specified wall thickness. So it's outside diameter, OD, if we abbreviate that as O as an outside and D as diameter, divided by T, which is divided by T, which is the thickness. So it's O, D as in Doug, divided by T, and the thickness of the wall. So outside diameter divided by the wall thickness, and that will be the basis for SDR. So for the SDR of the 26, 50 psi applies. As we are reducing the SDR, we are reducing the pressure rating. As we are, I'm sorry, it's the other way around. As we are reducing SDR, we are increasing the pressure rating, because when you look at the OD outside diameter by the thickness, as SDR becomes smaller, that means the thickness is higher. So because it's a thicker pipe, of course the pressure rating would be higher, meaning that they can withstand much higher pressure, as it is shown here. The pressure ratings are for water at 73 degrees Fahrenheit or 23 degrees Celsius, and of course for plastic pipe and the tubing, we can go as high as 250 psi or 1,380 kilopascal, as is shown here. Also, the hydraulic hose is of note here. Reinforced flexible hose is used extensively in hydraulic fluid power systems and other industrial applications. In that case, those applications require the pipe or the hose to be flexible. It must have that characteristics. As such, they are these materials. They usually include some kind of a rubber, whether it's synthetic, silicone, or other types, or some kind of a thermoplastic elastomers or nylons. Very important to realize the material that is used for some of these pipes. The reinforcement, of course, may be made of steel wire, Kevlar, polyester, and fabric. Remember, if the hose requires the flexibility, then one must pay attention to the reinforcement that goes into keeping the strength of the pipe and keep that in contact. The applications include steam, compressed air, chemical transfer, coolant. They use in HVAC systems. They use in cars, also in power steering fluids that we use in automobiles, propane, and again, water, food, and beverages. They are defined by SAE International Standard J517, if you're interested in that. The inside diameter of these hoses are 3/16, 1/4, 5/16, up to 4 inches. The pressure rating goes from 35 psig for systems that really doesn't require much pressure up to 10,000 psig. That's 240 kilopascal to 69 megapascal. Okay, now let's discuss the velocity of let's discuss the recommended velocity of flow in pipe and tubing and why they are important. Now, there are some factors that affect the selection of a satisfactory velocity of flow in fluid systems. Some of them we've already looked at, some of them we will, some of them we may not look at in this class, but they're all important. The type of fluid that flows. Of course, that would tell us the information about the viscosity and how the inner surface of the tube can be. The length of the flow systems. As we are sending the fluid through longer systems, of course, we are going to have more energy loss as the fluid flows. The type of pipe or tubing, because it would provide us with the level of friction that is required for that particular system. The pressure drop that can be tolerated. Remember that if we require a pressure drop at one point and the fluid starts at some other point, then of course we need to consider the pressure drop that needs to be tolerated here. The devices itself, if they're connected to pipe or tubing, these devices could be pumps, valves, etc. The temperature that the fluid is operated under, or the condition of the system, environmental condition, the pressure and the noise, very important. Sometimes in some facilities, noise is of great concern, so we want to make sure that is not the flow in the pipe is not noisy by itself. And trust me, rarely I've seen any system that addresses all these conditions efficiently. So if you look at the flow rate equation, Q equals A times V, and A being the area and V being the velocity. A is the cross-sectional area at the point under consideration, and V is the velocity of the fluid going through that cross-section. So if we would like to keep a Q constant, as we are playing around with A and V, of course we are going to, if we change one, we're going to affect the other one if we want to keep Q constant. For example, if we increase the velocity, okay, and if we have to have Q constant, of course A would be lower. So the area of the flow, the area of the cross-sectional area of which the fluid flows through would be less if we are increasing V, because we need to achieve constant Q, same results. If you want to change with these parameters and do a little parametric study. One of the important factors here is to keep the velocities low. If we, again, keep the velocities high, and that means we need to have much bigger pipes. So the cost would be a factor there. It could be cost prohibitive. So as much as we can, we need to keep the velocities low. Here's an example of a crude. Again, the word crude, C-R-U-D-E, is important here because we can only approximate the size of the pipe using this diagram. The discharge line, that's for the pipes that are using for discharge, and suction lines is for the pipes that are used for suction. Remember, we could have both of them depending on what side of the equation that we are dealing with, what side of the flow that we are dealing with. The volumetric or volume flow rate Q in gallon per minute is given on the x-axis at the bottom. On the x-axis on top shows the volume flow rate in cubic meter per hour, and this is for Schedule 40. The pipe sizes are also shown here. So if you have, for example, according to Schedule 40, a pipe size 4, and you want to see what should be the volume flow rate for a discharge line, you just continue this line. At some point, it's going to intersect this line, and then you read this number either the top or bottom. Of course, it's supposed to be a straight line, but my line is not really that straight, and you would read this. Let me give you another example. For example, at say a point, try to find a number. There you go. For example, for a size 1, Schedule 40 pipe size, the volume flow rate Q should be 15 gallon per minute. How do I know that? I continue this line, then I bring this down, and it's going to hit the 15 mark right here. If I'm interested in calculating the recommended volume flow rate up here, I'm going to continue that line, and it's going to be somewhere between 3 to 4. Again, there are different charts that are used for different schedule. One must be aware of that. These are experimentally developed, and they give us the crude, like an estimate of the pipe before we started. And later on, we need to grab the size, do the calculations, recalculate. It's really an iteration, and sometimes we need to go through a few iterations before we can get the absolute right size for the pipe. The recommended velocity of flow in pipe and tubing also could be as a function of volume rate, depending on the type of a pump that is used. We want to make sure that the capacity of the pump does not exceed the strength of the pipelines. Otherwise, we're going to have all sorts of problems, including breaking the pipes. We also want to make sure that the pipes are not too big with the specified pump capacity, because in that case we are losing a lot of energy, and the head loss would be pretty high. So we want to make sure that doesn't happen. Also, lower pressure can damage different parts of the system. It can also cause the erosion of the pump and the impeller surfaces. So we should always favor larger pipe size to achieve a lower velocity to an extent. Again, we don't want the pipe size to be too large because it could become cost prohibitive. Remember, pipes, they occupy a good amount of space if they are not underground, and it's important to realize all that. There are tables that can be used here, for example, for a volume flow rate of 10 gallon per meter, the suction line for a specific pipe could be size 1, and for that the velocity is given as 3.7. This is for the suction line, and for the discharge, as you can see, these numbers would be different because we want to make sure that we don't lose the required pressure there. Okay, I'm going to go a little bit quickly over some of these and get to the example problem. This graph that shows here applies to general fluid distribution systems, of course. Again, this is Schedule 40, and recommended range of velocity is given here. If you look at those, sometimes the range is, the upper bound and lower bound. The upper bound is almost 2 times or more than the lower bound. So one must also realize that as an important factor in designing the pipelines. Before I move on, let's talk about the U.S. Army Corps of Engineers. U.S. Army Corps of Engineers, they are one of the leading non-private organizations in the United States. They do much good work around the country and around the nation. The manual, they have different manuals for different types of, mechanical systems, civil systems, and what have you. There's a manual called Liquid Process Piping. It recommends, it has certain recommendations for normal liquid service applications. Again, these are normal liquid service applications, so one must realize how they define normal. So if it's really not for abnormal conditions, then we want to make sure that we study those conditions well before we can make a recommendations as to what would be the size of the pipe and so on. Let's take a look at the example problem. We are to determine the required size of standard Schedule 40 steel pipe to carry 192 cubic meter per hour of water with a maximum velocity of 6 meter per second. So first thing we need to do is we need to convert Q to cubic meter per second because of the velocity is given in meter per second, so we need to have the units correctly, and that is really the matter of converting 1 hour to 3,600 seconds and converting the using the conversion that's given here. There, we are going to pretty much calculate the area in the cubic meter. Again, these are simple arithmetic; they're not that complicated. It turned out to be as area as 8.88 times 10 to the minus 3 cubic meter. Okay. So, how do we interpret this? This is interpreted as the minimum allowable area because, of course, any smaller area would produce a velocity higher than 6 meter per second. So we must look at an appendix that's given in the book for a standard pipe with a flow rate just larger than 8.88, and that is right here. As you can see, I'm looking at one of the appendix right here. The flow rate, flow area is also given here. So according to that area, we're going to look up the flow area. So if you look at this table here and compare 8.88 times 10 to the minus 3 you'll see that the standard 5-inch Schedule 40 steel would fit here, right here, 1.291 times 10 to the, it's right here. This is what I'm referring to right here. Okay? I just marked it. So if you continue that, you would see it's going to take you to 1.291 times 10 to the minus 3, which is above 8.88 times 10 to the minus 3, but the size below that would be 8.82. So a standard 5-inch Schedule 40 steel pipe would apply. In that case, the flow area would be 1.291 times 10 to the minus 2 square meter, and the actual velocity, if we do the calculations now, this was the 1.291. This is the flow area that's required. Then, according to that, we see that the velocity should be 6.49 meter per second. This is the actual velocity. Okay, this is for a 4-inch Schedule 40 pipe with the flow area of 1.291. The previous one was with the 1.291. This is with the new one, 8.23. That is one below that. Okay, so this is if you look at the table, the 1 R velocity falls between these two numbers, 8.213 times 10 to the minus 3 and Schedule 5. So it falls between size 4 and 5. One of them I marked with a circle here as 4. So our number, our flow area would be falling between these two areas, and we need to calculate both of those. So we realize that this is too high, and we would go with the 4.13 meter per second as such. So this brings me to the end of the slides. If you have any questions or comments, make sure to send them my way via the course website. Thank you.